Good night, everyone, and welcome back to your channel Fundamentals of Engineering with Farhad. Fluid mechanics. In this example, we have like a nozzle and we want to calculate the speed of air leaving the nozzle, V air. So in this example, we have like a stream of an air at a standard condition comes to a nozzle, 2-inch diameter nozzle, and then strikes to a curved plate. We want to calculate the velocity or speed of the air when leaving the nozzle. In solving such problems, we need to consider the stagnation point at the stagnation tube, which we call it P naught, and also another point which is like the pressure of air, and work around the Bernoulli's equation to calculate or make a connection between the velocity and pressure to get the problem solved. We have like a airflow and also a manometer which is filled with water in connection with air. So in this problem, we want to solve a stream of air at a standard condition from a 2-inch diameter nozzle which strikes to a curved plate as you can see here, and a stagnation tube which is here connected to a water-filled U-tube manometer which is located in the problem. In part A, we want to calculate the speed of air leaving the nozzle, and also in part B, we want to estimate the horizontal component of force exerted on the vane here, R sub x. To start the problem, we can work around the Bernoulli equation, which we are looking for V air and also R sub x. Bernoulli's equation helps us get a start the problem with these 2 points. So P over gamma, which is P of air, and also here is we have like P air before entering the water, plus if we call the velocity of air entering air is V sub 1 squared over 2g is equal to the stagnation point, which is P naught over gamma plus V2 squared over 2g. So we are working for Bernoulli's equation about these 2 points. So we do know that P naught is a stagnation point. So we do have a P naught like stagnation pressure, and because at at 2 we have like a stagnation point, velocity is 0 at the stagnation, so it just we can simplify our equation and jot it down like P naught minus P is equal to rho g, which is gamma. This is the same formula for gamma times V1 squared over 2g. And if we just cancel out g in numerator and denominator, we can have it like P naught minus P is half of rho air times V1 squared. This is our first equation. So we got our first equation based off Bernoulli's equation between these 2 points. And then if we just look at the manometer tube, which is filled with water, in such case, we do know this point is before entering the water. This is P, and that's also P air. Air was coming to the nozzle, so it was pressure of air. And at the beginning, because there is normal air here, that's also P, pressure of air. So based off manometer, we can jot down P, which is P air, and as you move down to the water, the pressure decreases, plus rho gh for water, and that's equal to P2 at the other part. Mhm. So we can jot it down like P naught minus P is equal to this time rho water times G times H, and this is our second equation. And if we add equation 1 to 1 plus equation 2, we can mix them together, and that says a if we equalize the second part of these two equations, it just says a half of rho air times V1 squared is equal to rho water times G times H. And the only unknown of this equation is V1, and it just simply gives us V1 is equal to this parametric term. And if you do the math, it just gives you the V1 is equal to almost 175 feet per seconds. As soon as we have the velocity, entering velocity of the air to the nozzle, we can just move to the part B because we already calculated part 1, and for the estimate the horizontal component of force exerted on the vane by the jet. So if this is 30 degrees, this is 30 degrees, and it makes our alpha 150 degrees. If you remember, in liquid jet approaching the curved plate, we have already calculated. I can provide you with the link of this video at the end of this of our mm, video, and that says if you have such condition applied force to the curved plate, we can calculate the horizontal and vertical component of resultant force to the curved plate by Rx is rho q times velocity times 1 minus cosine of alpha, and Ry is equal to rho q v sine of alpha. So our case is Rx. So back to our problem, we can jot down the same equation. R sub x, or the horizontal component of force exerted on the vane, is equal to rho q v times 1 minus cosine of 150. And if you uh, replace qj by area times velocity, you can have it like r sub x is equal to rho air times area times v squared times 1 minus cosine of alpha. Vj in our problem is v1, entering velocity to the nozzle, because the other one was 0. And if you replace the numeric value for rho air, area of the nozzle, 2-inch diameter nozzle, times velocity, which we calculate in part A to be 175 feet per second, times in parentheses 1 minus cosine of 150 degrees, and it just gives us a r sub x is equal to 2.97. So in our problem, we were looking for velocity of air, which is 175 feet per second, and also r sub x, which keeps to um, hold the plate or vane in its location, and that's equal to Rx is equal to 2.97 pounds. Thank you. We will solve more problems to Bernoulli's equation and water momentum in next videos.